In this lesson, we are looking at special right triangles, specifically special right triangles that are 45, 45, 90 degrees. So there are two different types of special right triangles. This is one of them. There is another type of special right triangle that we'll talk about in the next lesson. So before we even get into the triangles aspect of this, we need to review a few topics. The first thing we need to talk about is reviewing square roots and how to simplify them. So if you have a square root, like the square root of 45, and you want to put it in simplest terms, in the simplest radical form, you can't do that using Desmos. If I type in the square root of 45, it's just going to give me a decimal number. It will not help me simplify that radical. So what we have to do is use our simplifying radicals process. That's where we look at the number that's on the inside called the radicand, and we break it up into two factors. Now the goal of factoring that number is to get the largest possible perfect square root. So remember, perfect squares are 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. So any number that is a perfect square, we want to see if we can make a factor out of those numbers. So 45 is divisible by 9 and 5. So 9 times 5 gives us 45, where 9 is a perfect square, but 5 is not. And that's perfectly okay, because we can't simplify 5 into anything other than 5 and 1. So 9 is our biggest perfect square. Now the reason we want this to be a perfect square is so that we can simplify it into a whole number. So when we take our perfect square factors, we split them up into two different radicals, and one of them should always be able to become a whole number. The other one, in this case 5, should not be able to be broken down into anything other than 1 times itself. Also with radicals, we also need to review rationalizing the denominator. So anytime you have a denominator, meaning you have a fraction, and there's a radical in the bottom, you're going to multiply the top and the bottom by that radical. So let's say we have this equation, and we want to solve this with a rationalized denominator. So pretty simple process here. We want to get x by itself, so we need to divide by the square root of 2 on each side. Now when we divide by the square root of 2, so that was this step here, then we can simplify that the square root of 2 over the square root of 2 is equal to 1. So that essentially what we call cancels out. So we're just left with 3 over the square root of 2 equals x. Now the problem with this is that we don't want to have a radical in the bottom. So we have to get rid of it, and we do that by multiplying by the square root of 2 over the square root of 2, because this is also equal to 1. So all we're doing is multiplying this fraction by 1. And when we do that, we're going to get to a place where there's no longer a radical in the bottom. That's the goal. So this is just, again, reviewing some things that we are going to run into when we're doing special right triangles. So we're multiplying by the top and the bottom with square root of 2. Then we multiply straight across. That gives us 3 square root 2 over. Now, when you multiply two radicals together, you're going to multiply the numbers themselves under the radical. So 2 times 2 gives us 4. And the square root of 4 becomes positive 2. That's the reason why we do this, is so that in the bottom we get just a regular number with no radical involved. Then it is possible, if these two numbers right there, if they have a common factor, then you would simplify those, but 3 and 2 don't have any common factors. So that's a quick review of simplifying radicals. Now going back to our review, we also need to talk about Pythagorean theorem, which I'm sure you are at least slightly familiar with. Anytime you have a right triangle Again, it's very important that that is a right triangle, so you need to see that little box there or be told that it is a right triangle. The two legs, so each side of a right triangle is technically called a leg, and then you have the hypotenuse, which is directly across from the 90. Each leg squared and added together, so a squared plus b squared equals c squared. That is your Pythagorean theorem. A squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. And finally, just talking about an isosceles triangle. So an isosceles triangle happens when the legs and the acute angles are congruent. Now, anytime you have a 45, 45, 90 right triangle, so if this is 45, then these two angles are congruent, which automatically makes them isosceles, because then it is imperative, it has to be that their legs are congruent. So you'll see those markings to represent congruency. So any 45, 45, 90 triangle is isosceles. All right, so we are going to actually discover the rule for 45, 45, 90 triangles and the ratio or the special relationship between all of their sides. So we're going to start with this 45, 45, 90 triangle here. If A is 1 and B is 1, so we're told that these legs are 1 and 1. What is the length of the hypotenuse? Well, if we were to use the Pythagorean theorem, a squared plus b squared equals c squared. In order to find c, all we'd have to do is plug in a and b. We know that they are both 1, so that's 1 squared plus 1 squared equals c squared. 1 times 1 is 1, so we get 1 plus 1 equals c squared. So that's 2 equals c squared. And finally, take the square root on both sides. So the square root of 2 is c. So c is the square root of 2. All right, now let's look at another 45, 45, 90 triangle. This time we have 2 and 2. Those are our congruent legs because this is an isosceles 45, 45, 90 triangle. Same process. In order to find the hypotenuse, we're going to use a squared plus b squared equals c squared. So if a is 2, that's 2 squared plus b is 2, so 2 squared equals c squared. 2 squared is 4, so that's going to be 4 plus 4 equals c squared. And then that gives us 8 equals c squared. Now if I take the square root on each side, this time I get the square root of 8 is c. However, the square root of 8 is not in simplest terms, so we need to simplify it. So what are two factors that go into 8 where one of them is a perfect square? I would say, just based on things that I know equal 8, by multiplying 4 times 2. So square root of 4 times square root of 2. Well, the square root of 4 is equal to 2, and then bring down your square root 2. So c is actually equal to a simplified version of 2 square root of 2. Okay, so are you noticing a pattern yet? Let's see if we find a pattern with this third one. All right, we have that a is 3 and b is 3. So a squared plus b squared equals c squared. A is 3, so 3 squared plus b is 3 equals c squared. So 3 squared is 9, so 9 plus 9 equals c squared. So that's 18 equals c squared, giving us the square root of 18 equals c. However, we want to simplify that. So what two numbers multiply to be 18? We could do 6 and 3, but neither of those are perfect squares. However, 9 and 2 does give us one with a perfect square because the square root of 9 is 3. So C is equal to 3 square root of 2. So between these three examples, we had that the legs were 1, the legs were 2, the legs were 3. Notice what the hypotenuse was. When the legs were 1, the hypotenuse was 1 times the square root of 2. When the legs were 2, the hypotenuse was 2 square root of 2. When the legs were 3, the hypotenuse was 3 square root of 2. So they all include that square root of 2, and the number that ended up being simplified in front of it was whatever the length of the legs was. So there is a rule. Anytime you have a 45, 45, 90 triangle, the legs, x, are always going to be whatever they are, and the hypotenuse is always going to be the leg times the square root of 2. So if the legs were 5, then the hypotenuse would be 5 square root of 2. If the legs were 7, the legs would be, or the hypotenuse would be 7 square root of 2, and so on. Now let's do a couple of examples using this information. So now we can kind of use that as a shortcut. Before, we didn't know how to use it as a shortcut. We had to use the Pythagorean theorem, but now that we know that rule, we can kind of cut corners a little bit. So here we have a leg that is 6. Since this is a 45, 45, 90, even though we weren't asked for it, we can say with confidence that the other leg is also 6. And the hypotenuse is always going to be the leg times the square root of 2. So the hypotenuse here is going to be 6 square root of 2. And that's all there is to it. Right, now let's find the leg if we are given the hypotenuse. So remember, we know that the hypotenuse is the leg times the square root of 2, right? Well, we don't know the leg, right, because it's called x. So the square root of 5, our hypotenuse, is whatever the leg is times the square root of 2. So we now have this equation that we can solve for x. This goes back to our simplifying earlier that we did with our radicals. So we need to solve for x. We have the square root of 5 equals the leg times the square root of 2. So we need to divide by the square root of 2. So that cancels on the right side. However, on the left, we have a radical in the bottom. And we don't want a radical in the bottom. So what we're going to do is we're going to multiply times that radical on the top and the bottom. Now when we do that, we're going to multiply straight across. So we're going to do square root 5 times square root 2. And when we do that, that's going to give us the square root of 10 over the square root of 4. Now we can simplify a little bit more. The square root of 10 can't be broken up because the only factors are 5 times 2 and 10 times 1. And none of those are perfect squares. However, we can simplify the square root of 4 to be 2. So we're going to have the square root of 10 over 2 equals x. So that is our leg length. It's the square root of 10 over 2. All right, let's try number 3. This time we are given the leg, and we're looking for the hypotenuse. However, the leg is a radical, and that's okay. We're still going to do the same process. The hypotenuse x is the leg times the square root of 2. So that gives us the square root of 3 times the square root of 2. And we just want to simplify that. That would be the square root of 6. And we can't break that down anymore because the only factors are 6 times 1, neither of those are perfect squares, or 3 times 2, which is what we already had, and neither of those are perfect squares. So square root of 6 is as simple as it gets. And finally, if we have the hypotenuse, we want to find the leg. We know that the hypotenuse is the leg times the square root of 2. So the leg in this case is x because we don't know it, so now we need to solve for x. Because we know that 6 is that leg times the square root of 2. So we're going to divide by the square root of 2. And now we're in a similar situation that we were before. So we can cross them out here. Square root of 2 over the square root of 2 is 1. So that gives us 6 over square root 2 equals x. Now, again, we want to get that square root of 2 out of the bottom, so we're going to multiply by the root 2 on top and bottom. And when we do that, we're just going to get 6 times the square root of 2 over the square root of 4 equals x. So we multiply straight across, and we got 6. So since that's a whole number, it stays outside of the radical. This does not become the square root of 12. Only if there's a radical on both of them. That's when they both go inside. So we have 6 square root 12, and then square root of 2 times square root of 2. That's when you're going to multiply them, and they go inside the radical. All right, now simplifying this a little bit more. 6 square root 2 over the square root of 4 is 2. And now we can simplify 6 over 2, which is 3. So this is 3 root 2 equals x. Okay, so that last step, let me go through that one more time. 6 over 2 is equal to 3. And that is how we use the Pythagorean theorem in addition to some radical rules and some radical processes in order to find special right triangle lengths in simplified radical form.